We often assume that if we can break a system down into its individual components, we will automatically understand how the whole machine operates. But extracting the parts doesn't always explain the motion. In foundational algebra, our primary method for understanding a polynomial is to tear it apart. We hunt for its roots, the exact values where the equation equals 0. Take a standard unfactored cubic polynomial. If we calculate a simple table of input and output values, we might accidentally stumble across a few primary x-intercepts. Once we extract specific coordinates, like x equals -2 and x equals 1, we can translate them directly into algebraic binomial factors, x plus 2 and x minus 1. Multiplying these together gives us a new quadratic divisor. We can then take that quadratic piece and perform algebraic long division on the original cubic polynomial, eventually yielding our final hidden factor, x plus 3. This rigorous mechanical process guarantees one thing. We have definitively identified all 3 absolute points where this specific function touches the horizontal axis. Plotting these extracted roots on a graph makes it feel like our algebraic mission is complete. We have precisely mapped the anchors of the equation. But algebraic extraction leaves us completely blind to the actual geometry occurring in the space between those points. Knowing exactly where a function intersects the x-axis tells us nothing about the path it takes to get there. At every intercept, there are hidden variables determining how the line behaves locally. Does the curve pass cleanly through the axis? Does it aggressively spike? Or does it turn back on itself completely? Standard point plotting fails to answer these questions. To guarantee the true global shape using a table of values, we would need to run an infinite number of calculations. The shape of the line, however, is not random. The exact geometry is actually coded directly into an algebraic property of the factors we just extracted. To map the total shape of a polynomial without brute force plotting, we must learn to decode the local geometric behavior at each individual intercept. Let's look at a new, factored polynomial engineered to display varied intercept behaviors. This equation yields 3 distinct geometric markers at +1, -2, and -4. This local geometry is governed by multiplicity, the exponent attached to the factor. At the x equals 1 intercept, the factor has an exponent of 2. Watch the curve enter from above, touch tangentially, and bounce back up. Because that exponent is squared, it forces this highly specific section of the overall polynomial to act locally like a foundational quadratic equation. This establishes the even parity rule. Any factor with an even multiplicity will always be tangent to the x-axis. The physical motion of the line is strictly constrained. It approaches the 0, touches it, and instantly reverses its vertical direction. And this geometric rule holds true whether the curve is approaching the axis from the positive top quadrants or the negative bottom ones. Even exponents act as rigid geometric force fields, preventing the polynomial curve from ever crossing into the opposite quadrant at that root.
Now, shift focus to the intercept at -2, which has a multiplicity of 3. Here, the line cuts entirely through the axis with a distinct S-bend. This reveals the odd parity rule. Odd multiplicities physically force the line to cross the horizontal axis. Contrast this with the final factor at -4, carrying an invisible exponent of 1. A straight line pierces the axis cleanly. A multiplicity of 1 is technically an odd parity, so it crosses. But it creates a direct, linear intersection with absolutely no curvature or hesitation. The visual geometry immediately tells you if an odd factor is greater than 1. If there is an inflection in the line at the intersection, the exponent is 3 or higher. Odd parity universally guarantees an axis crossing, but the specific integer size of that exponent introduces strict physical nuance into how that crossing curves. This raises a mechanical question. How do higher-order exponents, like powers of 4, 5, or 6, alter the curve's physical footprint on the graph? This split screen tracks a single 0 point as we scale the power upward. Let's examine the structural changes in the even polynomials first. The foundational x squared presents a standard parabolic bounce, requiring minimal dwell time on the horizontal axis. Contrast that with x to the 4th. The base of the tangent broadens, creating a visible hesitation before the curve rises again.
By x to the sixth, the line compresses heavily against the axis. It appears flat before vertically accelerating. We can apply this exact scaling logic to the odd powers. Watch the crossing behavior shift on the bottom graph. While x cubed presents a clean, sharp crossing curve, higher odd powers physically alter how the line approaches the axis. Functions like x to the fifth and x to the seventh retain their crossing symmetry, but they leave the zero incredibly slowly. This creates a distinct horizontal flat shelf before yielding to exponential vertical growth. The magnitude of the multiplicity acts as a precise visual fingerprint, explicitly defining the spatial compression and acceleration of the curve at every single root. Let's bring back our complex equation. We can now map its three disparate intercept rules simultaneously. Watch the single continuous line trace across the plane. The polynomial translates smoothly from left to right, locking into the specific behavior demanded at each coordinate: a sharp downward straight cross at -4, an upward S-curve cross at -2, and a tangential downward bounce at +1. All of these local behaviors stitch together perfectly to form one global function. By reading the algebraic parity and magnitude simultaneously, we instantly predict the total geometric footprint of the function without needing to plot arbitrary points. Standard rote point testing is a weak tool when dealing with complex mathematical systems. It gives you raw coordinates, but no context. True mapping requires a complete analytical protocol. Isolate the roots, determine the parity, and assess the magnitude. The specific curvature of a polynomial at its root is a physical manifestation of its underlying algebraic properties.